Why are we talking about the scientific method of stats class?
I have vague memories of hearing about the scientific method in high school science classes. It starts with defining a question and gathering information, then coming up with a research hypothesis, then testing that hypothesis by collecting data, analyzing the data, and then interpreting the data.
Oh, I bet that part about analyzing data involves stats.
There's even a tool in statistics called hypothesis testing. It results in a statistical conclusion, and that allows us to evaluate the research hypothesis and come up with a research conclusion.
Wait, you mean there's like a parallel world? Like there's a research hypothesis and a research conclusion as well as a statistical hypothesis and statistical conclusion?
Yes, except that it's sort of like the statistical world is embedded inside the research world.
Don't we just have one research hypothesis? It's weird because my prof talked about two statistical hypotheses, a null hypothesis and the alternate. Null refers to nothing, so I guess the null predicts that there will be no difference between the two conditions in the experiment.
That's the gist of it, but even more precisely, the null and alternative hypotheses are predictions about the parameters of the population. The statistical conclusion will be about those parameters. From there, you can evaluate your research hypothesis.
I don't really get that. What do parameters have to do with the conditions of my experiment?
Well, a null hypothesis usually says that two population parameters are equal. That's a quantitative way of saying that two groups are the same. The alternative hypothesis usually says that two parameters are not equal. The two groups are different.
That alternate hypothesis sounds like the research hypothesis.
Often, that's the way it is. So if the data supports the alternative hypothesis, then it also supports the research hypothesis.
Oh, but that sounds sort of like we're accepting the alternate hypothesis. But I think we're not supposed to do that. We're simply supposed to reject the null.
Oh, yeah, you're right about that. Do you know why, though? I've always thought that made things extra confusing.
Well, it helps to keep in mind that statistical inference is all based on probabilities rather than certainty. We reject the null when there's a very small probability that the null hypothesis is correct.
Oh, that's where the alpha comes in, right?
Yeah, the alpha is like a standard of improbability. We're asking ourselves, how improbable does the null have to be for us to reject it?
Oh, so that is why the alpha is usually a very small probability, like 0.05 or 0.01.
Exactly. So if there is less than a 5% chance that the null hypothesis is true, why would we assume the null? Instead, we would reject it. But notice that just because the null is very improbable doesn't mean we know how likely the alternate is.
It sounds like I have to juggle a bunch of possibilities because the null can be true, but we can reject it or fail to reject it. But also the alternative can be true, but we can reject it or fail to reject it.
Yeah. At the end of hypothesis testing, you can potentially be correct or incorrect. But you can be correct in one of two ways or incorrect in one of two ways.
Let me see. At the end of the hypothesis testing, you'll either reject the null hypothesis or fail to reject it. That we know for sure.
Right, we know our decision. But what we don't know is the actual state of the world. Either the null can actually be true or it could be false.
So let's say we decided to reject the null. If the null is true, then we have just made a mistake. If the null is false, then we're correct.
I believe that kind of mistake is called a false alarm or type 1 error. We decided there's a difference between two groups, but actually there isn't. It's like we decided to give surgery to someone who doesn't actually have a tumor.
Oh, let me try an example. A false alarm in an experiment might be saying that weight loss drug worked when the weight loss drug didn't actually work. I think that makes sense. That would be a pretty serious error on the part of science. But what if we fail to reject the null? Can't we still be correct?
Yeah, if we fail to reject the null when the null is false, that's a good thing. That's like saying that we don't want to perform surgery on someone who's perfectly healthy. Unfortunately, those kind of studies tend to be not published.
Yeah, because that's like saying that a drug didn't work when it actually doesn't work. Usually people are less interested in finding out what does not work.
Yeah, I think that's also why type 2 errors or misses are also seen as less serious than type 1 errors. For instance, if you say that a drug doesn't work, but it actually does work.
But I can't think of situations where that is a serious error too. I mean, what if we're just sitting on a drug that cures some big disease, but we rejected the null?
Absolutely. Type 2 errors are very serious as well. That's why you have to consider the ramifications of both type 1 and 2 errors when we're conducting experiments.
But is there a trade-off? Like, if we're going to tolerate some probability of false alarms, does it naturally mean that we are also increasing the probability of misses or something?
Let's think about that one. Another way of thinking about the alpha level is that it is the false alarm rate we are willing to tolerate. So when we reject the null hypothesis, we know there is a 5% probability that we are making an error because the null might actually be true. But we can never get rid of that probability entirely, so we have to make peace with a low enough rate.
So if we set the alpha at 0.05, it's like saying we are willing to accept that we might have a false alarm 5% of the time, because 5% of the time we're going to reject the null when it is true.
On the other side of the coin is 95%, but a 95% chance of what?
Oh, if the false alarm rate for rejecting the null is anything greater than 5%, that means it's too risky for us to reject the null. So that 95% of the time, we're not even going to reject the null. So if we fail to reject and the null is true, we're good. That was a correct fail to reject.
But going back to your question, notice that this false alarm rate doesn't say anything about our choices of making a type 2 error.
I guess that's because the false alarm rate assumes that the null is true. That's the only way you can have a false alarm error. If the null is false, then you cannot have false alarms. Wait, then, what is the p-value? Does that have something to do with false alarms?
The p-value is the probability of getting a sample statistic as extreme or more extreme given that the null hypothesis is true. So both the alpha and the p-value assume that the null is true.
Then what is the difference?
Well, the p-value depends on the sample stats. So, given that the null is true, we happen to get a particular sample. What is the likelihood of getting such an extreme sample? One that is so different from your null hypothesis. If it is highly likely, then the p-value is very high. And if it is unlikely, well, the p-value is low.
So I guess that is like saying that the p-value is the false alarm rate for a particular sample?
You can think of it like that. For instance, let's say we have a sample that has the p-value of 0.08. That's like saying we have an 8% probability of getting a sample that is this different, or even more different from the null hypothesis, given that the null is true. It's a pretty small.
But not smaller than 5%.
Right, because it's not smaller than 5%. We're going to play it conservatively and reject the null. We don't want to have an 8% chance of false alarm. We will only tolerate 5%.
But if the p-value is high, like 90%, it's like saying that the chance of getting this sample or a more extreme one is very high, given that the null is true. So it's sort of like saying your sample is highly likely in a world where there really is no actual difference among groups.
Which means you should accept the null hypothesis.
Ah, you mean fail to reject the null hypothesis.
Right.
You know, this helps because I can never remember whether the p-value should be smaller than or greater than 0.05. I realize now that I can just reason it out. It helps knowing what that 5% stands for.
And it helps knowing what p-value means.